Sorry it's so hot in here, by the way. I don't know why.
It's very loud out there, and it's going to make it hard to pick up stuff on the mic. Yeah.
Can we open the ventilator?
Still loud, yeah.
Maybe that one back. Okay. You're okay? Okay, well, we'll okay, Ryan's going to tell us about spectra. Sorry.
Okay, so for the second half of the sort of optical infrared talk, I'm going to focus on what exactly is the observational evidence that our process actually occurred in this binary neutron star merger, how much of it is. And so what we're going to do is we're going to start with near-infrared spectra for reasons that I'm going to explain, and try and figure out what they're telling us. And so you probably saw a figure like this. I stole it from the Caltech LIGO website. I guess it was originally made by Jennifer Johnson, about showing the relationship of the periodic table to the production of elements by various forms. And we are now going to conclude that our process, nucleosynthesis, is at least dominated by merging neutron stars. And of course, the question everybody who is not involved in this game then asks is, oh, so you saw some absorption lines of gold or something? And of course, that's not how it actually works. And so I'm going to give you a little bit of background into why we think this is a relatively high confidence statement. So I'm going to give the punchline first. And if you want to ask the question, what is the evidence that our process actually occurred in this event? Point number one is that we saw something in the infrared. It's so obvious that you might overlook it. But if you have some sort of transient that's expanding at a very high velocity, it will very rapidly lose its internal energy to adiabatic expansion unless there's an ongoing source of input of energy. And in normal type 1 supernovae, we appeal to radioactive nickel-56 to supply this energy. However, as Matt showed, everything about this object is inconsistent with there being a large source of nickel-56. And so we need another source of energy input to keep the ejecta hot and radiating thermally. And so something that produces a large number of radioactive elements with short half-lives is a very good candidate to do this. And step two is that based on detailed spectral modeling, SEE peaks near 1 micron are a consequence of lanthanide opacity that we don't see in other astronomical transients. And so to step back and explain where this comes from, I'm going to go back to this periodic table, which I put up originally. This was not just for the PR purpose, but it's worth thinking why we have a periodic table at all. And originally, Mendeleev noticed that there were patterns in the chemical behavior of various elements. We now understand that these patterns in chemical behavior of different elements reflect the fact that they have roughly the same electronic structure in terms of where their valence electrons are. So corner, they're S shell, over here they're P shell, D shell, F shell. And this very same chemical structure happens to affect the opacity that we see in the optical. So basically, when you have open F shells for an ion, you have a large number of available ways to distribute the angular momentum amongst the number of electrons that you have in that shell. And so there's many different ways to say the same thing, but this is a plot from Dan Caitlin's paper in 2013 showing the number of energy levels as a function of excitation energy for different types of atoms. And what he's showing here in yellow, you can barely see tin 2, which is a P shell atom, compared to iron 2, which is a D shell, compared to neodymium 2, which is an F shell. And so you have a much, much larger number of atomic levels available, which means that you have a combinatorically large number of possible atomic lines in which you will have some opacity. And to give an example, I took a line from this table from a recent atomic structure calculation by Tanaka et al., where they were analyzing neodymium-1, neutral neodymium, and in order to model the atom, that included 31,000 levels and over 70 million lines. And so this is ingredient number one for why it's hard to point to any little thing in the spectra to say this is the definitive spectroscopic consequence of a single. Ingredient number two is expansion. So this is now second nature to those of us who study supernovae. But for people who think more of static objects, you normally think about you have some stellar atmosphere, you have some bound transition, and you want to figure out whether or not a photon gets out. You have some opacity in that line, and you figure out the escape probability of a photon coming from the photosphere. But if you have an expanding ball of gas that has a velocity gradient, you greatly enhance the effect of line opacity. And the reason is if you have an explosion at a point, you will have material at different radii from that explosion. And in order to get to their larger different radii, that means they have to be traveling at different velocities. And that means that a bound-bound transition in one parcel of gas will experience a large Doppler shift relative to the other parcel of gas. And that means that a photon that is attempting to escape in some weak line transition has not just to escape from its current bound-bound transition, but it will redshift locally with respect to local standard of rest of all the other materials it tries to get out. And so the net effect is you have to consider not just how optically thick is any one individual line, but how many optically thick lines you're going to traverse as you escape the opacity, as you escape the ejecta. And this is something that we understand quite well in the context of type 1a supernovae, where the opacity is dominated by iron peak elements. And I took this plot from Jennifer's paper showing a bunch of different things. But what I want you to focus on, first of all, these purple and gray lines represent iron peak opacities in this expansion opacity formalism compared to some fiducial electron scattering constant opacity. What you see is at UV wavelengths, the iron peak opacity completely dominates. And that affects the spectral slope that we see in the UV at type 1a supernova. But because there's so many more lines in these lanthanide elements, the bound-bound expansion opacity greatly exceeds the electron scattering opacity all the way out into the infrared. So for material that has strong R process, including up to the lanthanide peak, these bound-bound line transitions dominate the opacity of the material. So I guess this was not officially realized until only about 4 years ago, or at least the first real calculations were done. And you can see from two different groups doing two different sorts of atomic structure calculations the same behavior in these two fiducial kilonova models. So in this case, this is just a toy model with, I think, 10⁻² solar masses of material, where you have iron opacity versus R process opacity. And you have sort of the same amount of material, same velocity, but the iron peak material has most of its opacity in the UV, which pushes its photons out in the optical, whereas the R process opacity is so strong in the UV to optical that everything is pushed out into the infrared with a color temperature of around 2000 Kelvin or so. And it's very hard to think of other astronomical transients that have color temperatures around 2000 Kelvin and are dominated by atomic lines. I mean, if you took a bunch of solar material, cooled it down to 2000 Kelvin and formed molecules. This is a very strange opacity to see in nature. And one thing I want to point out, that even in this toy model, there's a peak here at 1.05 microns, a shelf here at 1.2 microns, and a peak here at 1.5 microns. This model from Tanaka is very similar at certain epochs. Again, a peak here, a little longer to 1 micron, kind of a shelf, and then a second peak at 1.6 microns. So they've attempted to identify some of the dominant contributants there, but in these early work, the line lists were not as complete. And you can kind of see that because this is a log flux, and you can see it's really dying to the mid-infrared. And that's solely a consequence of the limitations of the line lists in those work, as far as I can tell. So next generation of models. Here is some recent work by Dan Case and collaborators that came out in conjunction with this event, showing how if you take a sort of fiducial model and you have some R process material, and you just change the lanthanide fraction. So this is parameterized by the fraction of lanthanides. So black, blue, green, red is going from 10⁻⁵, 10⁻⁴, 10⁻², 10⁻⁴ in terms of the lanthanide fraction. By greatly increasing the opacity, you increase the time scale, and you push all the flux out to the infrared. So this motivated the search for near-infrared spectra of a kilonova in order to look for the signatures of the opacity. And lo and behold, there's amazing agreement between the models and the data. And it's hard to impress upon people exactly how surprising this is that there's such great agreement between models and data. there are no kilonova spectra to test against to produce this. And the parameters of this kilonova model, there's a lot of stuff hidden in the, say, heating rate of the material, which we'll hear about in the following talk. But the three main parameters are some sort of mass scale, how much stuff you have, a kinetic energy scale. So I've labeled this with a velocity, but you should think about this as a kinetic energy parameter. What it really means is that this velocity is square root of 2 times the kinetic energy over the mass. There's a distribution of velocities in the material because you need that to have it a proper expansion velocity. And a lanthanide fraction of 10 to the minus 2. And you see a peak at around 1.05 microns, a shelf towards 1.2 microns, a dip, and a peak at 1.55. Exactly as we saw in the toy models from a couple years ago. Again, these models predated the data, and yet it agrees amazingly well. So if you try and examine how sensitive are these derived parameters within the context of a single family of models, we can just adjust each one of these parameters individually. So the red in each of the next 2 plots is our same fiducial model you saw in the previous plot, and now I'm just adjusting down the mass. As you adjust down the mass, the 0th order thing is you adjust down the flux. But because the mass also controls the diffusion time scale, the photosphere is at different locations within the ejecta for different ejecta masses, which causes different amounts of blending, which causes these peaks to shift around. So it's hard to self-consistently adjust the flux without shifting the peaks as well. Now you then ask, what is the characteristic velocity scale of this stuff? Well, you can start increasing the ejection speed, but by the time you get up to about 0.2 C, you get this green line here. Apologies to colorblind people. And you start rounding off everything, much like Matt showed in the visual. If you go up to 0.3 C, you have a very nice smooth spectrum. If you go down instead to something like 0.03 C, which is we just heard is kind of a low velocity disk wind, these peaks break up into individual subpeaks. And so this purple line here is a model where the velocity scale is much lower. So you can't have the dominant emission component be as slow as 0.03 C within the context of these models. If you have a disk wind, it just has to be faster. And lastly, the lanthanide opacity. So the red is our fiducial. If we go down to 10 to the minus 4 lanthanide concentration, you get this green line that's zooming up to the optical. That's something that's appropriate for blue kilonova. If you put it up too high, you actually suppress this peak relative to that peak. So this is not a precise measurement of the lanthanide fraction, I would say, but there's probably about a half a dex to a dex uncertainty within the context of these models. So yeah, so this is saying about the blue kilonova component. These are the same figures Matt just showed you. The blue kilonova component can only accommodate light R process, because any amount of the lanthanide series would suppress all that blue flux. And if you try and fit the models, you find very low lanthanide fractions, but you have actually worse agreement with the data, which is perhaps a sign that there's something more complicated going on in the blue component. However, it's also a sign that the neutron star merger produced material that does not have the heaviest R process material in addition to the heavy R process material. So it can produce the light R process. So then we tried to fit the spectral evolution over the course. These are our first 4 spectra. And at early times, there's some contribution from the blue all the way into the near infrared. And what I did was I just summed 2 of Dan's models for 2 different components with 2 different abundances. This is obviously not correct if there's more complicated geometry going on, but it's a 0th order approach to the problem. And at early times, it's actually even smoother than the combined blue plus red model, which means that most likely the photosphere is actually in this high velocity blue stuff, and you can't even see down to the red stuff. You can match these sorts of peaks out here, 2.5, 4.5 days, and by 7.5, it actually starts disagreeing again. But overall, this is remarkable agreement. So there's about half a dozen other groups out there with some degree of near-infrared spectra, all of which kind of look the same, which is good. And there's a total of, I think, 3 groups who are producing these radio transfer models for kilonova spectra. I compared to the family of models from Dan Kaysen, which is also Mansi Haswal and her paper. This is the original 2013 model, I guess, compared to her spectra. Over here, we have a couple of HST near-infrared prism spectra from Nora Troya and Neil Tanvir. You see the same pattern. It's at lower spectral resolution because it's HST prism, but there's no atmosphere, so there's some advantage. Over here are the two groups using the VLT and X-shooter, and they each did some radio transfer modeling. In the case of the Smart et al. Paper, they took the black body and they added cesium and tellurium to produce these two absorption features. I wouldn't put too much stock into that because it's hard to come up with a situation where only those two elements are dominant in decomposition alone. There's probably other elements in there. But I do want to focus a little bit on this nice mu spectra from X-shooter that were shown by Ellen Etienne. And two reasons. One is to show that her spectral sequence looks a lot like the previous spectral sequence I showed you. But she also compared to a different set of kilonova models. So Dan's models assume one zone with uniform abundances throughout. The two other groups, the Los Alamos group and Tanaka et al., are doing something a bit different. What they're doing is taking binary star mergers and looking at the outputs of those simulations in terms of velocity of ejecta and YE produced, and trying to self-consistently add up the flux from all of these different components. So in each of these panels, so these are the first four epochs, just like the previous evolution spectrum. The black is the data, and there's an orange component here, which comes from the tidal ejecta. And then there's blue and green components, which they come from disk winds. And they sum up to form the red. So black is data, red is model. And at early times, it's OK. As you go to late times, you see this very same shifting of flux to the infrared that we saw in the Kaysen et al. Models. But the comparison between the bumps and peaks, some of them are the same, some are slightly different. So if you want to ask what is the most robust conclusion coming out of spectral modeling, I would say the fact that all this flux is being pushed to the infrared seems to be relatively robust amongst all three groups. But the fact that there's differences in the models that come out is a little bit disconcerting. So it's hard to isolate exactly what the difference is because there's two things that have changed here. One is that the Kaysen et al. Models used a single uniform component, whereas these ones are attempting to actually include components with different YE. And second is each set of modelers has a different way of treating the opacity. It's not clear the differences that are coming out are due to the numerical techniques they use for evaluating atomic structure.
So I think the Kaysen group and the Tanaka group are actually in agreement as to the use of the expansion opacity, and I don't think the Los Alamos group.
Yeah, so the Los Alamos group is binning it differently. But
yeah, and I don't believe that they're advocating that approach anymore.
Okay, well, so some of the fits you have seen in the optical papers, not to the spectra, but to the light curves, we're using those models still.
Yeah.
Yeah, because one consequence of this issue about how you bin up the opacities is that the Los Alamos group for a while was pushing the flux even further out into the infrared towards the mid-infrared. And so that's one of the distinctions here. So I will defer to the theorists to settle that. But we come back to our original question is, can we identify actual detailed abundances due to specific elements? As I just said, that everything is blended together, it's a horrible mess. And you just turn the crank on the models. But Dan at least is optimistic, because if he takes his models, which by default, so peak near 1.05, shelf, peak, these all assume that the R process is produced in solar ratios. If you start monkeying around with individual elements, and neodymium appears to be the most important one, you shift where those peaks are. So it seems like it would be an amazing coincidence if you could get a model that looks so much like the data if you had the neodymium abundance incorrect. Now, maybe some of these other ones you can hope to constrain as well. But at the moment, there's enough uncertainties in what even the input atomic data are to have a layer of caution in interpreting any of this.
When we say atomic data, we mean numerical simulations of realizations of an atom.
Yes, yes.
We
These
don't
are
actually
statistical.
mean like experiment.
Yeah, it's not like NIST has a neodymium atom and it has a million different lines that they measure. These are statistical ways of treating the atomic structure problem. So what did we learn? One, the theorists were right, as much as it pains me to say that. But there's really actually amazing agreement between the vanilla predictions of the theory and what we actually saw. And I can give you a comparison here that in type 1a supernova theory, the two simplest theoretical models are pure deflagration and pure detonation. If you produced a spectral model from either of those, they would disagree with 80% of type 1a supernova out there. And so I view it as actually sort of a triumph that the initial models produce roughly the right amount of stuff with roughly the right amount of opacity. And we can just quibble about the details. To some extent, this is because of the very high velocities and very high opacities smooths out a lot of these uncertainties and what the underlying atomic data are, as long as it's roughly high enough. So basic predictions were borne out. One thing I didn't mention earlier was that if I take my first 4 epochs of spectra and look in Dan's library and try and find the best fit for each epoch, the best fit lanthanide fraction starts off being blue, then red, and steps back a little bit. So these were one-zone models, and you can imagine that in the real world there's a whole lot of variation of abundance fractions as a function of velocity within the ejecta. And this may provide a hint of what the dominant emission component each time is. And so all of the spectra are available from the Open Kilonova catalog or from the CFA group at kilonova.org, where you can just download tarball and start fitting them. Thank you.
Do you have any time for a few questions? Mariam?
So the question about the blue component. So you showed, very nicely the red part, but the blue one, what is this? What we've seen in other GRB systems and satellites, sharp breakout, which you have suggested for other GRBs. And I think something suggested that Timantha suggested that cocoon, sharper cocoon. Would you see the blue component because of that, because of sharp-heated material that you see?
It's unclear to me because those statements are based on fitting to the overall photometry. I'm not sure that they've actually gone to the step of creating actual spectra. And these spectra are a little weird looking. So it could be some way to fit that into the same picture. I'm not sure.
I think if you want to make the cocoon work, it has to be a really powerful jet because it has to compete. You're dumping in energy from the jet, and then it loses an enormous amount of energy to adiabatic expansion over these first few days. And the radioactivity starts taking over from that point. So you need to inject a lot of energy at early times. So we have to see, I think we have to try to see what's needed to explain the gamma rays, and maybe the cocoon will be powerful enough. But I think we need the jet to be, I don't know, I'm guessing you have to be like at least, several 10 to the 50 ergs of energy or something. It might be a bit high, but it's a possibility.
Can I say something?
Yes.
So we calculated this token model, but what in Mansi's paper, what we want to say is not really blue components coming from cocoon, but we may be able to explain the first data point, 0.5 days.
11 hours maybe.
Yeah. 11 hours.
You're not claiming that the 1.5 day blue stuff is cocoon?
Yeah.
Okay.
Maybe, but later on we agree that we see the blue kilonova.
Okay, Sarab and then we'll over here.
Talk about the ionization state, because a lot of the models it skips a lot of neutral stuff, but it seems surprising.
Yeah, it's a little surprising, but the temperature is actually pretty low once it's expanded. So it actually is at a few thousand Kelvin, not whatever it started off at MeV energies. So I think that's consistent, and you'll probably tell us more.
Okay, one more question from Jim.
Yeah, I just had a specific question. The lanthanide fraction is 1%. What is the bulk of what's the composition of the bulk of the gas?
It LiDAR process where the opacities have been, I believe, approximated by kind of iron group type opacities. So not every element has a full atomic structure. So you have to approximate by a few representative elements.
Okay, let's think Ryan again. I'm actually going to suggest, I'm going to cut my talk a bit short in the afternoon, so I'm going to suggest we take a coffee break now, and then we'll hear from Jenny after.